Many organizations treat Common Vulnerability Enumerations or CVEs as first-class citizens. Some even enforce strict SLAs on CVE remediation times depending on their severity scores expressed with a CVSS metric. Tools can now automatically analyze the code base across the entire application portfolio of an organization and create a full risk snapshot in real time. Finally, you would say there is a simple and quantitative mechanism to measure how secure each of your applications is. The numbers make sense as they are built on top of real and hard data. Moreover, attackers also have access to this data, so building your complete security strategy around vulnerabilities and CVEs makes absolute sense. Or does it? Well, from a scientific perspective, there are at least two key questions to investigate. First of all, how much do we trust the CVEs? In other words, do all CVEs represent actual security problems that need to be addressed? Secondly, how essential is the severity scoring? How much do we trust that? In other words, do all critical severity CVEs equal immediate high risk that needs to be addressed as soon as possible? In this episode, I will zoom into the science of CVEs and CVSS scores. I'm going to shed some light into who creates and manages the CVEs, as well as how they are scored and whether that really represents actual risk. I'm super excited about this episode, so buckle up and let's dive into it. Hi everyone, my name is Aram, and for the past 15 years I've been involved in application security as a researcher, industry expert, and lately as part of the OWASP SAM core team. Application security is really hard, and in this video series I would like to share some of my insights with you guys. After facing an increasing attack surface, incidents and breaches, organizations have finally started investing heavily in their application security program. An application security program is essentially a strategic plan focused on reducing security risk. At its extreme, if there is no risk, you don't really need application security. But unfortunately, there is risk, and security is also an elusive concept. It's not a feature that you're going to build and forget. There is constantly evolving threat landscape. So the key question in application security has turned into how do we measure risk and make sure that that risk stays below a certain acceptable threshold? Well, nowadays we have dashboards that provide a visualization of risk across the entire application portfolio, which turns complex security questions into crisp numbers and charts. Under the hood, these dashboards rely on tools that automatically scan the code bases for known and documented vulnerabilities. The data they use traces back to NIST, one of the most respected and reputable organizations and authorities in the field. It's a logical and quantifiable approach. It makes sense to prioritize CVEs, especially with high severity scores, right? But this is where it gets interesting. The raw numbers behind the dashboards might not really mean what you think they do. Let's start by talking about the Common Vulnerability Enumerations, CVEs. How are these indicators of bad news, I would say, created? Who manages them, and where are they published? A Common Vulnerability Enumeration, or a CVE, is essentially a publicly disclosed cybersecurity vulnerability. CVE is actually a CVE ID, which is a standardized unique identifier for every vulnerability formatted as CVE-year-number. Here is how it all works. A person or an organization discovers a vulnerability and reports that vulnerability to the CVE Numbering Authority, or CNA. I'll talk about CNAs a bit later. The CNA will verify the submission and then request a CVE ID from the CVE program. In addition to the ID, the authority will also create a CVE record with a short description, public information, and some references. The CVE ID is now reserved, but the CVE is not yet published and publicly disclosed. At this stage, there is only a CVE identifier available at the CVE program. Once the details of the vulnerability are ready, The CNA will submit the vulnerability details, and finally, as a last step, the CVE will be published for downloading and viewing for the public. So a CVE will have essentially a reserved status initially, and then whenever it's published, the status will change to published. CVE can also be cancelled, and it will get a rejected status. Now, the CVE program is managed by the Mitre Corporation under the sponsoring of CISA, which is the US Cybersecurity and Infrastructure Security Agency. Keep in mind, though, that CNAs typically do the heavy lifting. So Mitre essentially manages the database. The CVEs are created and largely managed by the CNAs. Originally, Mitre has been creating the CVE identifiers themselves. However, from early 2000s, they have created a first CVE numbering authority program, or CNA. The early CNAs were large corporations such as Microsoft, Oracle, and Red Hat. This allowed them to assign their own CVEs for their products. The CNA idea has rapidly expanded to include hundreds of CNAs worldwide. For instance, in Belgium, we have 5 numbering authorities, which is amazing for a small country like this. There's an important thing to note about the CVE numbering authorities, or the CNAs. We have CNAs that will be in charge of creating CVEs that apply to their own products. For instance, Microsoft, Oracle, Google, and so on. Aside from these CNAs, there are also the CNAs that we call CNA last resorts. These are a catch-all CNAs for vulnerabilities that belong to a product that doesn't have a dedicated CNA. For instance, vulnerabilities in many open source products would have to be reported to a CNA last resort. As you can imagine, there is a subtle difference between the vulnerability disclosure process to a dedicated product CNA, let's say Microsoft, and a CNA last resort. The CNAs that are in charge of their own products are likely to have a solid process in place to reproduce the issue and provide an early assessment of how impactful it is, how much risk does it carry. CNA last resorts are not maintaining these products. They don't have that much context awareness, or they are much less likely to be able to do that extensive validation. But let's park that conversation for a bit, and we will come back to this later. Overall, the whole flow of a CVE creation and management looks pretty solid. However, there are several problems with the CVEs, and in the next part of the video, we will discuss the most important ones. Remember the CNA last resorts? These are organizations who are a catch-all for vulnerability reports. They don't know the product in question, and they have very little context. So there is a disconnect between the code owner and the CNA last resorts tasked with determining the eligibility of a report for CVE. Without owning the code and the in-depth verification, it is extremely hard. And CNA last resorts are not bad actors, by the way, but they like to play better safe than sorry. So it's much worse not to create a CVE for a real vulnerability than to create one for something that might be a simple bug. So typically there will be much less strict in their validation efforts. This leads to the creation of many CVEs that are not really an issue. An interesting scientific study has shown that many of the CVEs that have been disputed are actually created by the CNA last resorts. The next problem with CVEs is that there is quite an incentive to report issues. As a researcher, owning a CVE is prestigious. The scientific community seems to be giving more weight to papers that have been based on a successful CVE submission. For security professionals, owning a CVE also helps with the resume. So there is a clear drive to create CVEs. However, it seems that the system can be gamed, as creating CVEs for the sake of it isn't really complicated. And that is largely related to the previous issue, where CNA last resorts are eager to create a CVE to make sure they haven't missed anything. Here is a nice story of a PhD student from Germany, Florian Handke, who tried to pull this out just for the experimentation reasons. He created a CVE that took literally a couple of hours. His CVE is for a deprecated system that nobody is actually running on the web. And he got a CVE vulnerability with the CVSS score of 9.1 assigned to him. Another interesting anecdote is the curl vulnerability that was assigned a very high CVSS score again. And by the way, we're going to talk about CVSS scores later on in this video. Curl is essentially a command to talk to websites or APIs using a terminal. Curl comes with a nice flag or option to retry the request to that website, to a specific website, with a certain delay. And that delay parameter may overflow. In human language, if you specify a very, very large number, instead of waiting for perhaps many years, it might retry immediately because the number grows from that very large number to very low number. That's the idea of an overflow. However, that is not a security issue. That is a simple bug because it has no impact. So you would wonder, why wouldn't the developer actually dispute that? Well, that brings us to the next issue on the list. Dispute process. Although formal mechanisms to dispute and reject a CVE exist, they are rarely used. Why? Well, because invalidating the bogus CVE is a real pain. And only after some serious backlash from the community is it typically possible to do so. Maintainers are aware of this and they don't even try, because it's actually cheaper to fix it. My tree will even typically mark the CVE as disputed and just leave it there. The effort to prove absence of vulnerability is pushed to the maintainer, who has to follow a multi-stage dispute process. Now, there is an interesting case study to illustrate also this process. So it concerns a CVE in a Linux kernel bug with the ID CVE 2019 12379. In 2019, the CVE was created for a kernel memory leak. According to the code owner, the problem had no impact, but the NVD gave it a medium impact. And we'll come back to the whole impact story later when we talk about the CVSS scores. The code owner has introduced a patch to it just to make it go away. And you'd imagine, hey, the story ends here, everything is good, right? Well, no, it turns out that the patch introduced an actual vulnerability, so the patch was reverted as it was the best decision. And the issue is still marked as disputed in the CVE database. Now, the next issue on the list is even a crazier one. Although, again, it makes sort of sense, and it goes back to the whole difference between CNA and CNA last resort. Remember, CNAs are in charge of their own products. And as opposed to CNA last resorts, they are way less eager and way harder to convince that there is an actual vulnerability, because CVs are bad for advertisement. Organizations who are CNAs for their own product thus are making your life very difficult to prove them that there is an actual vulnerability, which has led to the creation of something called notcve.org, where authors are disclosing vulnerabilities that are high impact and not recognized by the CVE numbering authorities. So these are the actual vulnerabilities that never ended up on the official CVE list. As I've mentioned earlier, CVE reporters, who are often researchers or practitioners like ethical hackers, are really proud to get a CVE published, and there is nothing wrong with that. It often has a real career impact. Unfortunately, this often leads to duplication and redundancies of CVE records. Many redundant CVEs are created for the same underlying bug, which artificially increases the number of CVEs. Schluger's paper illustrates that about 5% of CVEs they have looked at were actually duplicates, which is not a couple of entries here and there. Something related to this misalignment in incentives is the fact that after an initial CVE creation, the reporters just stop responding. They have published their paper, they have done their job, but the maintainers of the code get notified about the CVE, and that often comes in as a shock. Okay, so far I have talked about the various issues with the CVE creation and management and dispute process, essentially many of these problems are rooted in a major misalignment of incentives between the vulnerability researchers who want to get as many CVEs published as possible to pad their resumes, the CNAs who don't like creating vulnerabilities for their own products, and CNA last resorts who, on the other hand, don't have the capability for in-depth validation and are more eager to publish a CV. Now, a real challenge is also the cumbersome CV dispute process that the code maintainers almost never apply. I've provided various examples to illustrate how these issues can lead to the creation of meaningless CVEs, essentially noise in the CVE database. Now, the real question we want to answer is, how bad is this problem? What is the percentage of these meaningless or noisy CVEs? We still all remember major news headlines with Log4j, Heartbleed, and many other issues, many other CVEs that have costed billions to the industry. Well, it turns out that the problem is bigger than it seems. A recent Usenix Security Symposium paper by Schlugel and colleagues, which has been awarded Best Paper Award, examined the issue in depth, and their quantitative analysis showed that nearly a third of all CVEs were either unconfirmed or disputed by the maintainers. Now, to be clear, their dataset in this quantitative analysis is not a random sample of all CVEs, so we can't really claim that the results represent the entire ecosystem, because the dataset studied in this paper came from other scientific papers. Nonetheless, 1/3 disputed or unverified, that is not something that we could easily ignore or dismiss. Now, there is also a small twist, and this is remarkable to state, that most of the problematic cases, most of the noise, can be traced back to the CNA last resorts. So what are the key takeaways? First of all, the CVE program maintainers should put more attention on improving the quality and oversight of their CNA last resort. And they should also make sure that the dispute process is easier to invoke. Second, as a user of the CVEs, whether you're building dashboards, setting priorities, or running risk models, you should be mindful where the data comes from, and you might want to prioritize CVEs that are issued by the actual product vendors and not the CNA last resorts when you're assessing real-world impact. All right, so far we've talked about the potential noise in the CVE database. Unfortunately, that is only part of the problem. Things become more complicated once we bring in the severity scoring. Let's revisit the journey of a vulnerability from discovery to published CVE. It involves the CVE reporter and the CVE numbering authority that eventually publishes the CVE. But that's not where the story ends. After that, NIST analyzes the CVE and adds a severity score on top of that. By the way, NIST is not the only authority to create a severity score. Some CNAs may also do that. Here's an example of a CVE with two independent scores, one by Microsoft and one by NIST. It is also interesting to see that there is quite a disagreement between their scores, as Microsoft has given it a high severity rating, while NIST has given it a critical severity rating. But before we jump into that, let's first see what a CVSS score is and how it gets calculated. CVSS stands for Common Vulnerability Scoring System. It is an industry standard scoring mechanism for the CVEs, for the vulnerabilities. CVSS is actually a great idea because if we have 1,000 CVEs to deal with, and by the way, that's not exceptional, a scoring system to compare how urgent the problem is would really help us with a prioritization. There are various versions for CVSS, and the most widespread version is 3.1. To make things more complicated, version 4 was introduced as an answer to some criticism to version 3.1. It was introduced in 2023, but NIST isn't ready for version 4 yet. It's in sort of a preparation stage, so right now, version 3.1 is the one that is standard, I would say. Let's look at how CVSS scores are calculated. A CVSS score is essentially a vector of metrics. Each of these metrics comes from an ordinal scale. Ordinal scales essentially order the values without giving any more information on the distances between them. By the way, you can see my previous video on metrics right here, where I explain what measurement scales are and what an ordinal scale is. It has two values, low and high. And high means that the attacker has to spend some time and effort in preparing the attack to make it successful, to make the exploitation successful. Low obviously means that there is not much effort required and the attack can be easily made repeatable and automatable. In the ordinal measurement scales, we don't have any information about the distance between low and high. We can't say that low is 10 times easier than high, so there is no numeric relationship. And that is the case for every single metric in the CVSS vector. Let's take a brief look at the CVSS calculator. Essentially, to create the CVSS vector, we have to fill out several metric values. And there are three types of metrics: the base score metrics, the temporal score metrics, and the environmental score metrics. It is important to mention here that NIST will only publish and provide the base scores. The other two types of metrics and scores that are actually very, very interesting are left to the organization because NIST doesn't have the context information to get to these scores. To fill out the base score metrics, we have two subcategories: exploitability metrics and impact metrics, and the name says it all. The first part of the metrics are focused on what are the exploitability characteristics of this vulnerability, and the second part is regarding the actual impact. To create the CVSS vector, it's as easy as simply selecting the most applicable value for each metric. So for attack vector, we have network, adjacent, local, and physical. And I'm not going to go into the details of that. If you hover over each metric value, or let's call it a label, you're going to get a description. NIST also has a full documentation on how to create these metrics, by the way. You are not only going to look at these value descriptions here, but you will have to read the full documentation. Otherwise, you're going to come up with inconsistencies and potentially reliability issues. So to create the CVSS score, we are just going to select the most applicable value. Let's say we have vulnerability, it can be exploited remotely, it has a low attack complexity, we have low privileges required, and it means that we have some authorization, some level of user, but it's not an administrative user. We don't need user interaction, so we don't need to trick the users to do anything in order to run this exploit. And then the scope is unchanged, which means that the exploit is going to do some damages on the component itself. We cannot move laterally and go to other components and damage other things. The impact is, let's say it's a low confidentiality impact, it's a high integrity impact, and no availability impact. Once all these values are selected, we're going to see a CVSS score vector here, which is denoted with this cryptic tag. Now, you can see this is not a numeric value, which I guess most of you were expecting, and we will come back to that later. So there is indeed a heuristic to translate this almost unreadable thing to a numeric value, which you are probably used to see, which is a value between 0 and 10, but I will come back to that in a second. In the next part of this video, we're going to go and look through the scientific lens into potential issues when it comes to the CVSS scoring. First of all, translation of the vector, of the CVSS vector, into a numeric value. As I've mentioned, CVSS is essentially a vector of metrics, and each scalar value, so each metric in this vector, belongs to the ordinal scale. NIST has come up with a heuristic to combine these into a nice formula to provide a final value on a scale from 0 to 10, which is very, very handy. Because you can't really look at this vector and immediately get an idea of what's going on, how bad is the issue. This is why this heuristic has been created, so that you can have a single value telling you what is now the impact for a given vulnerability. Unfortunately, that heuristic is seriously flawed when we go back to measurement scale and mathematics based on these measurement scales. You can't really combine ordinal scales into a formula, and the reason for that is, like I've mentioned earlier, a low complexity attack has no relationship with a high complexity attack when we're talking mathematical terms. You cannot say a high complexity attack is 5 times more difficult or takes 5 times more time. By definition, ordinal scales do not allow you to do that sort of mathematics. However, by no means am I saying that this is a bad idea. It's a heuristic, and otherwise reading the CVSS score would be very hard, and it would make the whole CVSS largely useless, because it would be very, very hard to communicate in vector scores. People are not going to understand that unless you're very deep into the actual vulnerability itself. Now, on its own, this isn't too bad. But things get really, really crazy once we start to do additional mathematics on top of the CVSS scores. And that is exactly what many ASPM tools are doing when they are creating this risk score, which typically gets defined with a formula that looks like this.
We have a CVSS risk defined as CVSS times 1 plus EPSS times 1 plus 0.45 production plus 0.5 cloud, where CVSS is an impact score, a value between 0 and 10. EPSS is a likelihood score, a value between 0 and 1. Prod means, is this thing in production, yes or no? And cloud means, is this application or system internet facing the internet or no? And then asset risk would be the average risk for the top 5% or top 10% of vulnerabilities. That is how your risk score gets calculated.
And the formula does a lot of maths that honestly doesn't make sense. A more serious problem is the consistency of CVSS scoring. Here is an example to illustrate that issue very vividly. A remote arbitrary code execution vulnerability has been duplicated in the CVE database for whatever reasons, and it has been added 3 times. So this is the CVE, and it is exactly the same vulnerability. The first one has received a critical CVSS score, the second one has received a high CVSS score, and the last one has received a medium CVSS score. Again, it is the exact same vulnerability, and the CVSS scores are vastly different. The problem is that a lot of CVSS base metrics are open to interpretation. So you might decide that the attack complexity is low, while I might think that, hey, it is actually high. And studies have demonstrated that evaluators tend to disagree in scoring. What is more problematic is that the same study has demonstrated that the same evaluator will come up with a different CVSS score for the same vulnerability 9 months later. So not only are we going to disagree as evaluators of a certain vulnerability in our CVSS scores, but the same evaluator is also going to disagree with himself or herself later on in the timing. But why is this happening? How hard can it be to score a CVE using this simple calculator? It's a simple calculator, but it is a very powerful calculator, and there is a lot of additional context, a lot of additional documentation that comes with that calculator. Let's look at what are the reasons of consistency issues with the CVSS scores. Well, it turns out that CVSS scoring is very much context dependent, which means that the evaluator needs to understand how the application works. I told you that that is the case for temporal metrics and environmental score metrics, but that is also to some extent the case for the base score metrics, because we are going to come with an impact score, and to know what is the actual impact, we need to understand what the application does or what is the scope. Some vulnerabilities might not even have any impact. Let's look at this vulnerability that says that the current system, that the application in question, misses an HTTP only flag for the cookies, which indicates that the cookie is protected against cross-site scripting attacks. In simple human language, if there is a vulnerability of type cross-site scripting, the fact that the HTTP-only flag is missing would lead to the possibility of a cookie being stolen. But without an actual XSS, this issue has zero impact and hence a zero CVSS score. Another example is what we call a banner disclosure, which discloses the version of a particular web server or product ID or HTTP version. It doesn't necessarily have any impact on its own, and the CVSS should list the impact as none. Because simply saying this product runs version X does not necessarily mean that this is a vulnerability on its own. Although I have provided quite some examples and issues with the CVSS scores, I tend to agree with the phrase CVSS is like democracy. The worst system available except for all the other systems we have ever tried. I strongly believe that an average CVSS scores are not that problematic. Many studies also have indicated that even if the evaluators disagree in the CVSS scores, the delta or the differences are relatively minor. So the couple of examples I've presented here were, in fact, I would say the exceptions. But that leads us to the next issue on the list, and that is probably the most important one, that CVSS is not a measure of risk. It is only part of the equation, and actually NIST is pretty straightforward and explicit about that, and it says do not use this as a measurement of risk. A risk is typically expressed as likelihood times impact, and the CVSS scores are only measuring impact. So using impact as a proxy for risk is, I would say, not a great idea. Because basic third grade mathematics tells us that if likelihood is 0 or very low, the risk is also going to be very low, negligible, maybe 0. All right, what have we learned so far? First of all, based on scientific studies, a substantial chunk of vulnerabilities in the Common Vulnerability Enumeration database are never confirmed or even disputed. Hence, known vulnerabilities represented by their CVEs bring a certain amount of noise with them. We have also looked at the CVSS scoring system for these CVEs, which helps with their prioritization. We've established that the CVSS scores are mathematically flawed. They are also unreliable, as quantitative research has demonstrated that evaluators tend to disagree on the scoring. Even more remarkably, over 40% of vulnerabilities were scored differently after 9 months by the exact same expert. More importantly though, CVSS scores are representing only part of the risk equation. So the CVE prioritization requires additional context information from the application owners. But what does that mean when we go back to the idea of measuring and managing application security risk based on these CVEs? First of all, you should treat CVEs as signals rather than absolute truths. It is also a good idea to look into who has issued the CVE, whether it's a vendor CVE numbering authority who is in charge of their own product, or is it a CVE numbering authority last resort. CVEs from product owners are generally more reliable. Their CVSS scores are also more likely to be accurate, though I'm not aware of any scientific studies looking into that aspect of CVEs and their CVSS scores. Secondly, I would rethink the CVSS-based prioritization. I haven't talked about KEV and EPSS scores, both of which are metrics that measure the likelihood of a vulnerability being exploited. However, tools nowadays can also provide that information to help you out with the prioritization. Unfortunately, not many CVEs come with these KEV and EPSS scores. I would also combine the CVSS data with additional information such as threat intelligence and asset criticality. Finally, it is a good idea to introduce a semi-formal triaging process for the CVEs, which will help you again with their prioritization. Above all, a proper application security program should start with a clear and shared understanding of risk. A strong program will also prioritize threat modeling and a more practical and semi-formal triaging process for vulnerabilities rather than treating dashboards with vulnerability analysis as key aspect of their AppSec program. Once you have that in place, your team will know exactly how much attention should the vulnerability dashboards get. All right, that's all from me today. Thanks for watching this video. Ciao.